two things which are left out. One is problems related to oscillations, which I will be doing in next week. I'll announce the additional classes that I'll be taking. Then shock waves. Okay, so after this we will move on to shock waves. So today, what are the topics we will be covering? So today we will be seeing how the amplitude and phase of oscillation, in the case of forced oscillation, how it will vary with the frequency of the external force. Okay, again what we are doing is, it is the continuation of forced oscillation. Theory part is over. So today we will examine how the frequency and phase of the forced oscillation vary with, the case of forced oscillation vary with the frequency of the applied external force. Okay, so therefore recollect. So in the last class, what are the things we did? So I'll not get into too many details. I'll put in simple words. Okay, what happened in the last class? We considered the body which was executing a forced vibration. So what was the forced vibration? So the father was pushing the child. So he was pushing the child periodically so that the child or maintained in constant motion in the case of swing. Okay, so that force that we apply was given by what? F into sine of pt. So that force that we apply was given by F into sine of pt. So then, so as usual, the theory and all is clear. So you found what is the resultant force, you apply Newton's second law of motion, then we introduced new variables omega 2b, then we solved the equation, the solution, then finally we ended up getting this expression. So which was that? One is the expression for the amplitude of the forced oscillation, which is given by this. Next, the phase lag is given by this equation. So therefore equation 12 and equation 13, these are what are going to be our starting points. Okay, so therefore amplitude A and frequency omega, these are found from equation 12 and 13 respectively, which we have to plug in this equation 7. That is here, if you plug in, you are going to get a big expression. Okay, so therefore let us move on. Today what are the things we are going to study? Today we will be studying how the amplitude and phase varies with the frequency of the applied force in the case of forced oscillations. So before we proceed, as usual, I always start with some interesting videos and then we move on to concepts, right? So therefore let us watch this video that talks about resonance, and then we will see the consequence of variation of amplitude. Okay, okay, so just see here again same thing. What is that? It's a spring mass system. So the frequency is varied by using a signal generator. Okay, so it's Friday again, so yeah. So in this example, or in this video, what you are going to see is, so there is a body of mass m which is attached to two springs, and so this will vibrate anyway. So here what you see here is, it's a signal generator in which you can vary the frequency of the signal generator. So when you vary the frequency, that is when you increase say from 2 hertz to 400 hertz, somewhere around 3.3 hertz, the body is going to vibrate at a very large amplitude. Okay, that is what is given in this 3 minutes of demonstration. Okay, so therefore let us move on to this, and then we will apply this concept and understand it in a better way. Okay,
so clearly time for some physics fun. What I've got set up here is a vibration generator. So the pin here will move up and down. I have a spring, and that's a spring with a K of about 30. And then I have a 100 gram mass, and I have a second spring attached to a clamp stand that's out of shot. So it's a dead simple experiment to do. We have the signal generator at the back here, and at the moment I've turned down the amplitude. So I'm going to turn up the amplitude, which is hidden, and we're going to put it on maximum, and hopefully you can clearly see that this pin now is vibrating at a frequency of 2.06 hertz. Now let's see what happens if we dial down the frequency. We're now going at 1 hertz, well, nearly a hertz there, 1 hertz frequency.
So if the frequency is vibrate, if the frequency of the signal generator, that is external force, happens to be 1 hertz, you see that it just simply vibrates, okay, or almost nil. Then from here, if you increase the frequency, what will happen to its vibration? So let us observe that.
Up and down, okay. Let's go up a little bit. We'll go slowly, so you can clearly see, getting a bit more motion with that mass. And I've done a scale on the back here, and this is in centimeters, so it's every 2 centimeters. I did a bit of a line at the mid value. Now it's not perfect because I'm on a bit of an angle, but it's not really designed to do an accurate display. We're just looking for an overall effect. So 2 hertz, pretty much the same thing is happening. So let's go up a little bit more. There we go. 2.5. Seems to have died off now. There's not a lot happening. 2.7, 2.8, 3 hertz. Interesting. Wow. 3.2, 3.3. Crikey. The amplitude is massive. Looking at least 14 centimeters. Well, let's just go up a little bit more. 4. Oh. Oh dear. It's died off. 4.4.
Okay, you see here that the particle or the mass vibrates at a very high amplitude, at a very maximum amplitude, when the frequency is around 3.3 hertz, and when the frequency is increased beyond that, so that is when you increase, say, from 4 or 4.5 hertz, the amplitude of oscillation comes down. Okay,
5. 5. Oh, it's gone. That effect has gone. Let's go back. Now, I think it was roughly around the 3 point. There we are. 3.3. We're roughly looking about that. So we're clearly seeing a resonance effect. So what we're actually talking about is that when the frequency of the periodic force applied, so the force that's applied here to the mass spring system, equals what we call F naught, or the natural frequency, large amplitudes of oscillation occur, providing the damping is light. Now, the periodic force needs to be in phase with the velocity, so force and velocity in phase of the oscillating object. This occurs when the displacement, so the displacement here is pi by 2, or 90 degrees out of phase with the periodic force. Now, as the applied frequency becomes increasingly larger than the natural frequency of the mass spring system, you saw clearly, didn't you, that the amplitude of the oscillations decreased more and more. And if we put it right up, you saw that that was the case. There was that peak point.
okay, I think you got an idea. So in this example, you see that the frequency of the mass spring system is varied using this signal generator. Okay, it was varied from 1 hertz to around, say, 5 or 6 hertz. So you see that when the frequency is increased somewhere close to 3.3 hertz, the mass vibrates at a very high amplitude. So therefore that you actually call it as what? Resonant frequency. So therefore today we will see how the amplitude and phase of the oscillating system varies when you vary the frequency of the applied force. Okay, so I think we'll move on. Okay, so therefore today what we are going to discuss, the following. What is that? It is the dependence of, so what we are going to discuss is the dependence of amplitude and phase of the oscillating system when the frequency of the applied force is varied. Okay, look here, the frequency of the applied signal, the frequency of the applied signal in our, it is denoted by P. Okay, so as the frequency P of the external force is varied, the response of the vibrating system also varies. So that can be put into broadly three categories. Okay, so they are, one is P, the frequency being very much less than omega if the applied force is less than omega. Next is when the applied force P comes very close to omega. Next, when the applied force P happens to be far higher than omega. Okay, what does that mean is, for the spring mass vibrating system, the natural frequency of vibration omega, we already know it is given by omega is equal to k by m. Therefore, that is fixed. So when you vary the frequency of the applied signal, so the response of the vibrating system will also change. So how it is, how will that change is what we are going to examine, and that can be put into broadly three cases. What is that? One is when the applied frequency happens to be quite less when compared to natural frequency of vibration. When the applied frequency matches with the natural frequency of vibration, that's the second case. The third case being when the applied frequency P being far greater than the natural frequency of vibration. Okay, so look here, today we will deal more with respect to the qualitative study and not with the mathematical part. Okay, what does that mean? Okay, first look here, the key equations that we derived yesterday are this. Okay, so which is, one is the amplitude of vibration, one is the amplitude of vibration, and the other is the phase of vibration. Okay, one is the amplitude of vibration, other is going to be the phase of vibration. So phase of vibration, let me put it here, that is this. Okay, tan alpha equal to this, or alpha is tan inverse of this, they all one and same. Okay, the second one is this, I'll just decrease its size. Okay, so this is equation 1, and this is going to be my equation 2. So what does that mean? What does that mean is, look here, this is going to be my equation 1, and this is going to be my equation 2, or equation 12 and equation 13, in whatever way we label it. Okay, next, what is the first case? First case is when the applied frequency happens to be less than the natural frequency of vibration. In my demonstration, I mean in our demonstration that we saw in the YouTube, one uh, the signal generator was initially set at 1 hertz. So 1 is obviously less than 3.3 hertz. So that is going to be this. So if omega, if P is far less than omega, then what will happen? If P is far less than omega, then for example 2 is less than 1000, 2 is less than 1000. So if P is far less than omega, what will happen? Some terms can be neglected. So therefore what will happen? This expression for amplitude A and alpha, they will simplify as the expression for amplitude. Expression for amplitude is equation 12, and expression for phase is equation 13, which is this. So 12 and 13, they will simplify as follows for the first case. What is that? So I will not get into mathematical details. We'll look at it in the qualitative point of view. So what will happen to the amplitude? Amplitude will simplify as A is equal to F by M omega square. Okay, amplitude will simplify as F is equal to A equal to F by M by omega square. And what will happen to the phase lag? Phase lag is given by alpha is equal to tan inverse of 0, which is this. Okay, so therefore once again I'll repeat, what is that? If the applied frequency, if the applied frequency is very much less than the natural frequency of vibration, so this equation 11, equation for amplitude, that will simplify to this, and the phase lag tan alpha, phase lag for tan alpha, that will simplify as this. Okay, tan alpha equal to 0, or alpha is tan inverse 0, which is equal to 0. Okay, what does that mean is, you can see here that from this expression, okay, so from here you can see here that the amplitude of vibration depends only on frequency, sorry, it depends on F, that is mass, then the amplitude of the external force, and omega. So that is, amplitude will not depend on the frequency P of the applied signal. It will not depend on the frequency of the applied signal. So what will happen to the amplitude? Amplitude will not depend on P, that is frequency of the applied signal. Also, alpha is equal to tan inverse 0. What does that mean is, the applied force will be in sync with, the applied force will be in phase with the displacement of the object. Okay, displacement of the object means what? I will put it in simple terms. Okay, there is a time lag which we call it as either phase. Okay, so in this case what happens, if the frequency of the external signal is very much less than the natural frequency of vibration, then the amplitude of the system will not depend on variation of P. It depends only on F, M, and omega square. That's all. That is the intrinsic property of the system. And also the displacement is going to be in phase with the frequency of the applied force. Okay, in phase means what? I'll put in simple words. Okay, see, generally we all eat sweets. Okay, for example, for someone his favorite sweet may be Mysore Pak, or for someone it may be jangri, or for someone it may be jalebi, or someone from Bengal
Jamun.
it may be Kheer Kadam. Okay, so look here, generally what happens, the moment you eat your favorite sweet in your mouth, you will feel that sweetness, you will sense the sweetness sensation immediately. That's what I mean by telling that phase is 0. Okay, clear? So that is about this. Next, case 2. Case 2 is what? If P is equal to omega, then omega square is equal to P square. So now let us get on to the second case. Okay, so second case means what? I don't want the other stuffs. I'll just remove all this. Okay, so what is case 2? Case 2 is this. Okay, so here what will happen? So if P is equal to omega, if P is equal to omega, omega square minus P square is equal to 0. If P omega square minus P square is 0, what will happen? A will be equal to F by M into square root of 4B square P square. Therefore, amplitude A will be equal to F by M divided by square root of 2bp. That's all. If this term is 0, only this is going to contribute. Therefore, it's going to be what? F by M whole divided by 2 into bp. That's what gives rise to this equation. Okay, so the amplitude of vibration is going to be F is equal to F by M into 2b omega. So I'll place it here. Okay, so let me place it, say here. I think it is easy to visualize. I'll place it here. That's going to be amplitude. And what will happen to the phase? Look here, phase is given by alpha is equal to tan inverse of 2bp by 0, which is pi by 2. Tan inverse of infinity is pi by 2. So I'll put it here. For example, let me put it here. Okay, so look here, if omega is equal to P, can you see here? So let me take the brush. Okay, so if omega is equal to P, omega square P square is omega square minus P square is 0. Therefore, 2bp by 0 is what? Anything by 0 is, any finite quantity by 0 is infinity. Therefore, you see that alpha will be equal to tan inverse of 2bp by 0. What is tan inverse of infinity? It is pi by 2. This is actually pi by 2. Okay, 90 degrees, pi by 2. Okay, not pi, it is pi by 2. Okay, therefore in this case what happens? So when the applied frequency approaches the natural frequency of vibration, the amplitude of the vibrating system is maximum, and there will be a maximum transfer of energy from the external force to the vibrating system. Okay, what does that mean is, if the child is swinging in a swing in a park, okay, and if the father pushes in such a way that his frequency, if it matches with natural frequency of vibration of the spring, then there will be a maximum transfer of energy from the external force to the vibrating system, and hence the amplitude of the system is going to be high. Okay, and this phenomenon we call it as what? When the applied frequency matches with natural frequency of vibration, then this we call it as what? Resonance. Okay, this we call it as what? Resonance. Okay, once again I'll repeat. If the applied frequency matches with natural frequency of vibration, natural frequency of vibration is given by omega equal to square root of m by k. That's all. So if the applied frequency by chance, if it matches with natural frequency of vibration, then what will happen? Then the amplitude of the vibrating system is going to be maximum, and this phenomenon we call it as resonance. And there will be a phase lag of pi by 2 between the displacement and the applied force. Okay, so what does that mean? What does that mean is simple. So you are having your favorite sweet Kheer Kadam, for example. So you have just had in your mouth, but you will realize the sweet sensation only after say 2 minutes. Okay, very late you will realize this sweet sensation. So that delay we call it as what? Phase lag. That is going to be pi by 2. Pi by 2 means it's actually 1/4 of the time period. Okay, it is 1/4 of the time period. So therefore, what does that mean? So that is cause and effect. There will be a phase lag of 1 t by 4 or pi by 2. Okay, what does that mean? What will happen first? That is cause. So what is that? You have just put your favorite sweet, say Kheer Kadam, into your mouth. So after a time period of t by 4, after a time gap of t by 4, capital T by 4, or a phase lag of pi by 2. So after some 2 or 3 minutes, you will realize the sweet sensation. That's what we mean by phase lag. Okay, clear? Therefore, now look here. So there are a lot of advantages with resonance. So generally in a hanging bridge, whenever the military soldiers march on a hanging bridge, they don't do march fast. Why they don't do march fast is, if they do a normal walk, so the hanging bridge will not vibrate. So if they do march fast, what will happen? The hanging bridge may vibrate. So sometimes by chance, if it coincides with one of the modes of vibration, then the hanging bridge may vibrate with a large amplitude and it may break. So to avoid the damage or to avoid resonance, the military soldiers, whenever they walk across an hanging bridge, they will not do march fast. That is in order to avoid resonance. Okay, I'll give one more interesting application of resonance. What do you mean by resonance? If the applied frequency matches with natural frequency of vibration, there will be maximum, the amplitude of the vibrating system is going to be maximum. Okay, look here once again, let us look at that video, earlier video. So this was the link. Okay, let us look at that video again. So what do you see? For example, here, yeah, can you see here, when the frequency approaches close to 3 hertz, it will start vibrating with a maximum amplitude.
3.3.
Okay.
Crikey.
So
the amplitude is massive. Looking at least 14 centimeters.
okay, so around 3.3 hertz, the body is vibrating with a larger amplitude. Okay, so therefore when the applied signal, frequency of the applied signal matches with the natural frequency of vibration of the vibrating system, the amplitude of the vibrating system is going to be high.
Looking at least 14 centimeters.
Okay,
Let's just go up a little bit more.
and this is called resonance. Okay, just to give you an idea that music, so people like music, right? So to relax, so music has an healing touch. So in order to demonstrate that, I have this following mythological story. Okay, following mythological example, an anecdote or an example coming from a mythological story. Okay, what is that? Let us look into that. Okay, this is again an illustration of resonance, or we say that Music has an healing touch. Okay, just observe this. I'll just tell the background of this and then we will see what happens. Yeah. Okay. So the background of the story goes like this. Okay, so can you see here? Here is a person. He's actually a sage. Okay, it's just a mythological story. Okay, here is a sage. So he will be cursed by some Gandharvas from heaven. Okay, he would have done some mistakes, so because of that he would have been cursed. Okay, what he has been cursed is, so he, except his head, the whole of his body is going to be converted into a stone. Okay, now what happens is there will be, so therefore this sage will be under this curse for quite long time, for say couple of years. Okay, so what happens is, once a king, he happens to pass into that forest, and he will notice this sage who is whose head is just there above the stone, and his entire body is submerged, or the entire body is sandwiched inside a stone. So he finds it very strange and unknown. So he interacts with that. He then what he does, he will be interacting with he'll be interacting with that sage. He will tell what happened to you, how come you got into this status. Then he will narrate all his background story. Then the king will tell, how can I relieve you from this curse. Then the sage will tell that no one, so even if you bring a big metal and hit this rock, this rock will not break. But what can one do is, so there will be a couple of musical instruments which is there below a tree in front of this stone. Okay, so if anyone who plays all those musical instruments, and because of those musical vibrations, they will be able to make this stone to vibrate, and eventually the stone can break. So that is one way. Only through these musical instrument is what I can be relieved from this curse, is what he tells. Okay, therefore that king, what does that king do? That king will try to play all those musical instruments, and that is what is the narration of this song. Okay, so now we'll walk through this one, say under 45 seconds of this song, and see what happens. Okay, and this song is there in several languages. Okay, it is there in Telugu, it is there in Kannada, it is there in Hindi, it is there in Tamil. Okay, in Bengali also it is there. You can just find out its counterpart in the other languages. Will not worry about the meaning of this song. All you have to understand is, so as at the end of the song, what happens? Applied frequency matches with natural frequency of vibration. Then what will happen? Let us see. Okay, let us see. So you can see that when the applied frequency comes very close to the natural frequency, the stone is start vibrating. Okay, so let's see whether the stone will vibrate with a large amplitude, and then see what happens. Okay, so I think you got an idea. What is that? So you got an idea. What is that? So in that story, you see that in that song, you see that when the frequency of the musical note, when it varies, what will happen to the stone? The stone will start vibrating. Now, as the frequency approaches the natural frequency, you see that the stone vibrates at a larger amplitude and finally breaks. Okay, and that's give rise to, that is what we call it as resonance, and eventually that sage is relieved from its curse, from his curse. Okay, so therefore that is one interesting analogy of application of resonance. Okay, and we also can see, for example, if an aircraft or a jet, if it moves at a very high speed, even if it moves at a altitude of say around 10 kilometers, you feel those vibrations. That is, in our home, our window panes will vibrate, correct? If there happens to be a fast moving jet, so same thing. So when the music is created, so there are chances that the stone also can vibrate, and there are chances that a stone can also break. Okay, provided it's a closed chamber. Okay, so therefore that is about the second case. Now we'll move on to the third case. What is the third case? The third case is, so therefore what is resonance is clear. So if the applied frequency matches with the natural frequency of vibration, then the amplitude of the vibrating system is going to be very high. Okay, so there will be a maximum transfer of energy between the applied force and the external force. Okay, next what happens? Case 3. What is case 3? If the applied force happens to be far higher than natural frequency of vibration. So I'll take this. Okay, so okay, I'll remove all other stuffs. Okay, now look here, this is the third case. So if P happens to be far higher than omega, for example, 1 lakh is greater than 10, or 10 crores is greater than 5. Okay, so if P happens to be far higher than omega, then omega square minus P square will be as good as P square. Okay, in that case, what will happen? What will be the expression for amplitude? Amplitude and phase, they are going to be like this. Okay, this is the expression for amplitude. I'll put it here. Then this is the expression for phase. Phase is given by what? Alpha is equal to tan inverse of minus 0, which is pi. Okay, this is pi, not pi by 2. Okay, kindly understand. Okay, let me put it here. Now if I choose brush, okay, look here. If P happens to be far higher than omega, then omega square minus P square will be same as P square. Okay, for example, 1 crore square is greater than 25. Therefore, the difference will not hardly matter. So omega square minus P square will be as good as P square. Okay, so then what will happen? Look here, this term can be neglected. You have only P square here. Then in that case, the amplitude A will simplify to this equation, that is A is equal to F by M whole divided by square root of 4B square P square plus P power 4. That's all. Now look here, what happens here in the expression for alpha here, tan alpha is equal to 2BP by minus P square. So what will that be? This will translate to tan inverse of minus 0. So tan inverse of minus 0 is pi. Okay, so therefore what is the time difference between the displacement and the applied force? That will be half of time period, or the phase lag of pi. Okay, what does that mean? What does that mean is, I'll put in simple language. So cause and effect. So pushing the object is the cause. When the effect is going to take place after a duration of pi radians, or after a time period of after a time of t by 2, half the time period. What does that mean? You have taken your favorite sweet, say kheer kadam, so you have put in your mouth. Okay, even after 2 minutes you did not feel its sensation. So almost after 5 minutes you kept on chewing, and when you are about to swallow, your tongue will sense the sweetness of that kheer kadam. So therefore there is the time lag of 5 minutes, no, that we call it as what? Phase lag of pi between the displacement and the applied force. Okay, so that therefore this is the third case. So here what will happen, that is the thing, and that is what you see, that as when the frequency, applied frequency, is greater than omega, then the amplitude will depend on frequency of the applied force. That depends on this. That's all. Okay, next, what is the significance of resonance? So that is what I told. When the two frequencies, when the applied frequency matches with natural frequency of vibration, there will be a maximum transfer of energy between applied force and the vibrating system. Therefore there will be a maximum transfer of energy, hence the vibrating system is going to vibrate with a large amplitude. Okay, that is done. Next we'll look at the sharpness of resonance. So what do we mean by sharpness of resonance? So sharpness of resonance tells you how the peak will increase near the resonant frequency. Okay, so therefore what is sharpness of resonance? I'll take this here. Okay, I'll eliminate all other things I don't want. Okay, so what is sharpness of resonance mean? Okay, so look here. What is sharpness of resonance? Sharpness of resonance means, so the rate at which the change in amplitude occurs near the resonance depends on damping. Okay, so how fast the amplitude, how quickly the amplitude changes with the change in frequency of the applied signal, that is what we mean by sharpness of resonance. If the damping force is large, then the rise is going to be very slow. If the damping force is small or nil, the system will quickly rise to, the amplitude will quickly rise. Okay, therefore how is that summarized? I will put it here. Okay, before that, this sharpness of resonance, this concept I'll just tell. So what is sharpness of resonance? Sharpness of resonance, it gives you the measure of the rate at which the amplitude changes corresponding to a small change in the frequency of the applied external force at the stage of resonance. Okay, what does that mean is, amplitude is denoted by A, frequency is denoted by P. Therefore that variation of amplitude with external frequency of the external signal means what? It refers to dA by dP. That's all. Okay, so everything is summarized in this one single graph. I will consider this graph and I will tell you what is the effect of damping. Look here, this is the graph we have. Okay, so what is the effect of damping? So look here, I'll put in simple words. Can you see here? If the here B is equal to 1, here B is equal to 2, and here B is equal to 3. Okay, that is, as the damping force increases, what will happen? The curve is going to become more and more flat. Okay, the curve is going to become more and more flat. Okay, more and more flat means what? Can you see here? The curve is going to be more flat like this. It will be more flat like this. More flat means what? Bandwidth is going to be large. Okay, bandwidth is going to be large. On the other hand, if the damping, if there is no damping force, or if the damping force is less, how does the curve vary? How does the amplitude vary with how does the amplitude vary with the frequency of the external force? So I will show that by, say, green color curve. Okay, I'll show that by a green curve. Okay, can you see here how will, if B is very small, how the amplitude will vary? So can you see here, it varies roughly like this, quickly. It will be very narrow. Okay, can you see? Just varies like this. Okay, can you see here? Once again, I'll repeat. In the green curve, when the damping force is very small, green curve represents a sharp peak. Okay. On the other hand, if the damping force is high, if the damping force happens to be high, then the curve is going to be flat, and the curve is flat as shown. Flat means what? It is like this, very straight. It will be spread over a large bandwidth. The curve will be very flat. Okay, therefore sharpness of resonance is inversely proportional to damping. Okay, it gives you the ability of the material or this vibrating system to vibrate despite of the presence of damping force. Okay, this is done. This part is done. Next, we'll move to, so that's all. So what is the effect of damping? One can notice from the above figure that the curves are flat for large values of B, and hence resonance is flat. On the other hand, the curve for small values of damping force, it exhibits pronounced peak or a narrow peak. Okay, fine. Next is Helmholtz Resonator. Okay, Helmholtz Resonator, what happens? Okay, look here. So all of you have seen, you can actually produce sound. You can actually produce sound by blowing a bottle. If you take a bottle, if you take an empty bottle, you can, if you blow air, sound will emerge from it. Okay, for example, okay, can you see? Let us look at that in the following example. Okay, so let us look at in the following example, Helmholtz Resonator. Even how does the flute work? A flute, a musical instrument flute, it also works based on this concept of resonance. Okay, you are just blowing air, so when certain things matches, it produces a melodious sound. Okay, now look here. We'll go to,
Hi folks, I'm going to explain why when you blow over the hole of a bottle like this, you hear a specific sound. One that's different for different size bottles. Something called a Hi folks, I'm going to explain why when you blow over the hole of a bottle like this, you hear a specific sound. One that's different for different size bottles. Something called a Helmholtz resonance. On a related note, I'll also explain what part the speaker had to play in this other video. In there, I'd shown you how to make these bottles move using only sound from the speaker. First, Helmholtz resonance and making sounds by blowing in bottles. The bottle has to meet some minimum requirements. It has to have a large volume called the chamber, as well as a narrower volume called the neck, and a hole at this end of the neck. When air is forced into the bottle, like if we just blow into the opening, the air pressure in the bottle is increased. For a while, the air in the neck of the bottle acts like sort of a massive plug, pushing inward, building up the pressure. We can compare this to a spring with a mass at one end. The air in the neck is like the mass, and the air in the chamber is like the spring. The air in the neck moving inward and compressing the air in the chamber is like the mass pushing on the spring, compressing the spring. At some point we run out of energy and the compression stops. The energy is all gone into compressing the air. At that point the process reverses and the air starts to decompress, forcing the air in the neck back out. This pressure decrease continues and even goes too far as the pressure inside the bottle becomes slightly less than the room air pressure. Since the pressure inside is less than room pressure, the higher room pressure forces air back inside the bottle. That continues until it overshoots and the air pressure inside the bottle is again compressed. It then reverses again, and so on. But each time the compression and decompression is less, with less and less energy to drive it, until finally it stops. The air pressure inside is the same as the air pressure outside. But that cycle of air going in and out happens at a consistent frequency, determined by things like the speed of sound in air, the cross-sectional area of the neck, the volume of the bottle here, and the length of the neck. Basically this formula. This frequency is called the resonant frequency. More specifically, this is Helmholtz resonance, and the bottle is called a Helmholtz resonator. If you're just blowing on a bottle to have it make a sound, the sound you hear is a sound wave made by that air moving in and out of the bottle. And as I just said, the frequency depends on the geometry of the bottle. So that's why the sound is different for different size bottles. What part does the speaker play in making these bottles move? It emits sound waves at the opening, at the bottle's resonant frequency, the same frequency we're just talking about. How did we choose that frequency? We chose it by blowing over the hole in the bottle and recording the sound made by the air in the bottle as it compressed and decompressed, as we described. We then examined that sound on the computer and found the frequency of that sound. We then told the computer to emit that frequency out the speaker. So the speaker is emitting sound waves at the bottle's resonant frequency. Why do we do that? Well, in this case, the first sound wave from the speaker blows into the bottle and starts the first compression and decompression going. But since the speaker is emitting sound waves at the right frequency, just as the bottle is starting its next compression, along comes another sound wave to add energy to that compression. And it again adds energy to the next compression with the next sound wave, and so on. The speaker is keeping the compression and decompression going by adding energy each time. And that's Helmholtz resonance, why you hear a specific sound when you blow on a bottle, and the role of the speaker in this acoustic propulsion. Well, thanks for watching.
Okay, you can see there.
Showing how to move the bottles using sound. Another on how to make a lift or ionocraft that flies using ion propulsion. And one on
So you could have seen in that video that by just blowing the air, it leads to compression and elongation of the air. So compression and elongation of the air is nothing but what? Rarefaction, and correct. So that produces waves. So when blowing of the air, by chance, if it matches with the natural frequency of the vibration that is determined by the volume, then we will hear a loud sound. Okay, that is what related with the construction and working of an Helmholtz resonator. Okay, so today, in order to, if you have a musical instrument, in order to tune the strings of a, say, sitar or violin, you have lot of application, I mean app are developed in the handset which you can download. So again, this is based on what? Resonance. Okay, so tuning. So there are lot of musical apps which will help us to tune our musical instrument at right frequency. So therefore, how do you measure the quality of a sound? We measure the quality of a sound using Helmholtz resonator. That's one of the important application of Helmholtz resonator. What is that? To measure the quality of a musical note. Okay, therefore that's about this. So again, it is the same stuff. It's almost the same thing. What is that? I'll just briefly tell in few sentences. So what is the Helmholtz resonator consists of? Look here. So the Helmholtz resonator is this. Okay, so I copy this. Okay, so this is the Helmholtz resonator. Okay, so I will put it in simple words. Look here. So earlier what happened? We had a glass. We had a glass. The glass in which what happened? Both ends were closed. I mean, this end was closed, but only this end was open. Okay. Now in the case of Helmholtz resonator, what happens? This is roughly the geometry of an Helmholtz resonator. So this end A, we call it as mouth. Then this will be the body of the resonator, correct, as shown in the diagram. And this point B, which is a narrow opening, this will be, so look here, you will place this near your mouth and blow air inside it. Okay, and this end B is kept near the ear. This end B is kept near the ear, or it will be connected to, say, an spectral analyzer, which is going to analyze the quality of the musical note. Therefore, what is this? Here is the place you will give input, and this is the place where we will have output. This is the place where you will have output, and this output will be used to measure the quality of an musical note. It could be your blowing air. It can also be sound vibrations that are coming from a musical instrument. Okay, now how does this work? Put all this, look here, same thing. So when we blow air, if I use red color, so if you blow air inside, what will happen? The air inside this will be set into compression. So the air will travel in the downward direction. So when this end is near this end, what happens? Part of the air bubbles will be reflected back. So therefore, that will lead to what? A compression and rarefaction. So, or it leads to vibration of air molecules inside this Helmholtz resonator, inside this container. Okay. Now, so when this happens, so a loud sound will be produced at the other end. Okay. So this we call it as what? So the same thing what happens in the working of whistles or sound produced by blowing air in glass bottles. So these are few examples of Helmholtz resonator. So the natural frequency of vibration of the bottle, that will be given by this expression. What is that? It will be equal to the frequency with which it vibrates. That depends on the volume of the bottle. So the volume of the bottle is V. So you see that the natural frequency of vibration omega is inversely proportional to the volume of the bottle. So therefore, if volume of the bottle V is known, then the frequency at which you get maximum amplitude can be evaluated using this expression. Okay, of course K is a constant that depends on what kind of air that is there inside this medium. Okay, so therefore this is briefly the construction and working of the Helmholtz resonator. If you just merely blow air, so the air column inside the resonator will be set into vibration, and if the applied frequency matches with natural frequency of vibration as given by this expression, then the amplitude, you will hear a louder sound emerging from the resonator. Okay, so this is briefly this. So in the next class we will move on to solving problems related to Helmholtz resonator. Therefore this completes almost entire theory along with mathematical derivations as far as the oscillations and waves chapter is concerned. Okay, next class we'll move on to shock waves. Okay, so I will stop here. If students are having any questions, you can ask, or students having any queries.